Before we get into the specifics of the Taylor series approximation for multivariate functions, I want to take a look at a couple of preliminary ideas that to some extent may feel like review, but when we get into it, there's just some notation that I think is best to have ironed out ahead of time. So first of all, remember we looked at the term tensor, and that's just a multi-dimensional array. And the important part is that we're going to be able to, and actually it's going to make a lot of sense to reshape the tensor into a vector. So let's say that we have a 3 by, let's go 4 by 3 by 2. So essentially what we have here is we have a 4 by 3. We have 4 rows and 3 columns. So I'm just going to represent this as that 4 by 3 matrix. Now the fact that we have 4 by 3 by 2 is what makes this thing a tensor. And what we should see here is that there's actually a second layer to this. So it's as if instead of just having one 4 by 3, we have two 4 by 3s kind of stacked together. So let me draw this so that you can kind of see what I'm talking about here. Notice that we have 2 layers going back in the rear direction, right? So here's our 2, and that 2 is this dimension here. Notice that there's 2 layers, and each of those layers is a 4 by 3. So here we have one 4 by 3, right? This is our one 4 by 3. I'm giving it a little bit of depth here, but that's my one 4 by 3 right there, right? There's the actual 4 by 3 that we see at face value. And then we have another 4 by 3, which is this stack back here, and that's just kind of glued on. It's another 4 by 3 glued to this 4 by 3. Well, what I would rather have is instead of having 2 4 by 3s, I'm going to create out of this a stack of 2 4 by 3s. Okay, so I'm going to make it into one matrix, and instead of having 4 rows, 1, 2, 3, 4, I'm going to, because I have 2 of those, I'm going to give this 8 rows. So 1, 2, 3, 4, 5, 6, 7, and 8. So what I'm going to do is I'm going to stack my second 4 by 3 right below the first 4 by 3. So here we have our first 4 by 3, and then down here we'll have our second 4 by 3. And here we have 1, 2, 3. So this becomes an 8 by 3 because all we did is we took one of our 4 by 3s and stacked it directly below it. So it didn't change the number of columns, it just doubled the number of rows. Now that's already much easier to work with, but I would prefer to have a vector out of this. So there's a number of ways that we could actually construct these, a vector out of this matrix, but you can see that we have a total, I'm just going to try to find a color here. You can see that we have a total of 8 times 3, we have 24 values that we need to represent. Notice that 4 times 3 by 2 is also 24. That's not a coincidence, right? Because we're taking 24 cells and we're just trying to rearrange them. So the way I'm going to do this, forgive me here for this orange line, the way I'm going to do this is I am going to go row by row, and each row will become a column itself. So this first row will become my first column. And that's just going to be a 3 by 1 column. Okay, so we go across the rows, and this is just the convention. It makes things work out nicely. Then my next row will be another 3 by 1, and then I'll have another 3 by 1 below that. And hopefully you get the idea now. I'm just going to go dot, 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 until our last row here. And that will be our final 3 by 1. And well, how many of these 3 by 1s will we have? Well, we have 8 3 by 1s. And if we have 8 3 by 1s, that makes this vector a 24 by 1 vector. Okay, so that way we're working with vectors, and we can work with vectors instead of having to work with these multi-dimensional arrays. Just a convention, it'll make things work out nicely as we go. Now the next thing we need to deal with is summations. And remember that summations add things up. And in this case, here's a summation. It's adding 2 times I. Okay, well, what is I? Well, I is an index. And the index is stated down here. That's the index. It doesn't have to be I. It's just kind of like saying, you don't have to use x for a variable all the time. And this is the start value of I, and this is where the value of I ends. Okay, so the way this works is we start at the start value of I. So for I equals 0, we're going to get one term, namely 2 times I. So 2 times 0. And then we add to that the next term, which will be for one I value greater. And the indices cannot be less than 0, and they do not go backwards, they only go up. Okay, and so for I equals 1, 2 times I will be 2 times 1. And then for I equals 2, we'll have 2 times 2. And finally, because we get to I equals 3, that's our stopping point, we'll have 2 times 3. And now you can add these all up. You'll get, let's see, 6 plus 6, I think this comes out to 12. Okay, that's a single summation with one index. But what we're going to be dealing with soon is multiple indices. And this could represent where, for example, we're working with a matrix. And in this case, notice I have Aij. So let's define a matrix that's actually going to be 3 by 2 here. 1, 2, 3, 4, 5, 6. And I'm just going to equate this to what we're going to refer to these elements. This is A11. This next one is A12. So first index is the row, and the second index is the column. A21, A22. A31, A32. And so let's think about what this summation does and how it works. So first of all, the first index is set. Okay, so we're going to start with I equals 1. Next, we move in to the second index, which is j, and we start at the lowest index for j, so j equals 1. So for that combination, I equals 1, j equals 1, we are going to add Aij, so A11, I and j are both 1, and we're going to add I to it. Okay, well, what is I? I is 1. Okay, so what would A11 plus 1 be? Well, A11 is 1, and we're taking 1 plus 1, which gives us 2. So I'm kind of moving upwards here to show what these minimize to. Now, how do we deal with the next value? Well, there's at least a couple of ways to do it, but what the normal way to do it is to keep the outer index the same and increment through all of the inner indices. This is the inner index right here. So what I'm going to do now is I'm going to stick with I equals 1 because there is another value of j, which is j equals 2. So for I equals 1, j equals 2, we'll have, okay, this is added, because remember we're adding terms together, A12 plus I, which is 1. Now that would mean we take 2 plus 1, which is 3. So we would have 2 plus 3, so far gives us 5. All right, well, notice that j is maxed out. We've reached the maximum index for j. So at that point, we increment the I index, so now I becomes 2, and we reset the j index back to 1. So we'll have I equals 2, j equals 1, and then we'll have I equals 2, j equals 2. That maxes out our inner index, so now we'll say, okay, let's go back to I. Well, I can still go up. It can go up to 3. Now notice that I is maxed out. So I can't go any higher than 3, but j resets to 1, and then for I equals 3, j resets to 2. Now I'm not going to write out these terms, but you can imagine this will be A21, which would be 3 plus, now I is 2, so it would be 3 plus 2. I equals 2, j equals 2 will be A22 plus I, which is 2, so that would give us a 6. I guess we could write them down, right? And we're adding these, right? We're adding these to the ones that we already have. So 2 plus 3, here we'll get I equals 2, j equals 1, just 3 plus 2 is 5. I equals 2, j equals 2, which is 4. 4 plus I is 6. 3, 1 will be 5. Plus I, which is 3, 5 plus 3 is 8, and then 6 plus 3 is 9, and you can add up 2 plus 3 plus 5 plus 6 plus 8 plus 9, and that should give you your total. which, I mean, we're here, we might as well do it. 5 plus 5 is 10, 16, 24, and 33, if I've done my math correctly. Okay, so that's how we deal with two indices. And again, that could be for a matrix. But what about a tensor, right? Well, for a tensor, imagine that what we have here is a matrix stacked upon a matrix. So imagine that what we have here is we have a 3 by 2. That's where our I and our J goes, but K could actually represent the multi-dimensional dimension. Okay, so this will be like our 3 by 2 for K equals 1, and then we'll have another 3 by 2 for K equals 2. So imagine, again, having like the two 3 by 2s stacked together like this. So here's our first layer. And then imagine that all we do is we extend this out and stack a second layer on there. So what this summation is effectively going to do is, again, we start with I equals 1, J equals 1, and then we always focus on the inner index. So K equals 1. We won't go through all of these, but let's again assume that we have some elements. So I equals 1, J equals 1, K equals 1. That would be this very first element here. And then we would go through all of the innermost indices. So then we would have a term for I equals 1, J equals 1, K equals 2. Okay, so K equals 2 would just be this element right here. And then we would go I equals 1. Notice that we're out of K's, so we move outwards one summation, and now we increment J. So we're going to go through all of the J and K's for I equals 1. So now J becomes 2, and we reset K to 1. Then we go I equals 1, J equals 1, K equals 2. So that's as if we are now in I equals 1. That's going to be the first row, second column of the first matrix. And then we'll go I equals 1, J equals 1. I'm sorry, J equals 2, K equals 2. That will be this value right here. So essentially we're using the same elements across the two different dimensions. Okay, what do we do next? Well, now notice J is maxed out. J has reached 2. So we've run through all of the J's and the K's for I equals 1. Well, now we're ready to go to I equals 2. Reset J to 1, reset K to 1. 2, 1, 1. Now we'll go 2, 1, 2. And then we'll go 2, 2, 1. Finally, we'll go 2, 2, 2. So you notice that this was up here. This was for I equals 1. This is for I equals 2. That had 4 terms. There are 4 terms here. There are 4 terms here. So we'll also have 4 terms for I equals 3, J equals 1, K equals 1, and so on. And that'll give us a total of 12 terms, which makes sense because 3 times 2 is 6, times 2 is 12. So we'll have 6 elements in the first layer, 6 elements in the second layer. And that's predominantly how we add tensors together, or how we deal with tensors is we can represent it as a triple summation. Now you can go quadruple summation, it just gets much more tedious. And so this is as far as we need to go here.